Okay, YouTube, in our last video, we explored what we call normal distribution of data. And we say that data that's normally distributed, has this bell-like curve where the average, if we use this model of a perfectly normally distributed thing, the average is right in the middle and 50% of the population lies to the right of the average and 50% lies to the left. What we want to do in this video is look at how we could use, say, some data that we've actually collected to make some predictions about the likelihoods involving a population. And so what we're going to look at here is modeling using our standard normal distribution, or our normal distribution. So we say the scores for a state's peace officer standards and training test are normally distributed. So what we're told first off the bat is that these scores were normally distributed, and we're also told the mean is 55 and that our standard deviation is 12. So it says that these test scores range from 0 to 100. What we look at here basically then is something where we want to start by writing down the average in the standard deviation. So our mu, or our mean, is 55, and I'm just going to label this here points. And we are told that our standard deviation, this little O with a tail on the right side there, sigma, our sigma is 12 points. So what we're going to do basically, first of all, is sketch the normal curve that applies to this situation. So the cool part about this normal curve is that we always sketch the same stinking curve. That is to say that for part A right here, let's go ahead and put in our x-axis, and what we're going to do is we're going to make this normal looking curve here, this bell looking thing up on top. And with respect to sketching this in, we always put in our average first, and I'm going to go ahead and label this here. We're going to say that this is our average. I'm going to label that with mu, but we're going to go 3 standard deviations above the mean. 1, 2, 3, and we're going to go 3 standard deviations below the mean. We're going to try to evenly space these. Now, the interesting thing is, because we were told the value of the standard deviation here, 12, then we could just say 55 plus 12. This would be the next step up. We'd say 12 units above that score, the average score, would have been 67. If we go 12 above this, grabbing our calculator, we say plus another 12. We would get 79, okay, so 79. And then in terms of 79 plus 12 here, we would say 79 plus 12 would be 91. So 91. Now going down by 12s, if we were to take 12 off of 55, we would get a 43 in this case. Take a 12 off of this, we get a 31. And 12 off of 31 here, we say 31 minus 12 would give us a 19. So basically what we're seeing is that this is kind of what our population of test scores would look like if it's based on what we saw in our sample. And so I do want to label these down here also. These are our test scores. So to answer questions on parts A and B, let's read the question first of all. It says, about what percentage of the people taking the test have scores between 43 and 67? So the thing we're going to do here is this. Excuse me. After we've sketched the normal curve, then what we're going to do is highlight or shade the portion of the curve between the critical values, critical x values. Now in terms of our critical x values here, what they're asking here is about what percentage of the people are that have taking the test have scores between 43 and 67%. For part A, I'm going to write this here. I'm going to write this as 43 is less than or equal to x is less than or equal to 67. And essentially what I want you to see is the probability that we grab somebody that had a score between here and here is the same as the percentage of people that had a score between there and there. So when I say let's highlight or shade the portion of the curve between the critical values, we can see that 43 lies here and also 67 lies here. So when we shade this, we'll just draw a line here to trap off these subsections, but we could see that it would be the percentage of people that lies between here and here. Now, knowing our empirical rule, we know that first of all, 68% of the data always lies within 1 standard deviation of our mean both ways. Now, that being said, we could also say that we know that 34% of the data lies in each of these subsections, but the bottom line is we could say that about 68% of our data lies between there and there. And so the likelihood that somebody took this test and got a score between these two scores would be 68%. Now on part B here it says an agency in the state will only hire applicants with test scores of 67 or greater. So about what percentage of the people have test scores that make them eligible to be hired by the agency? When we look at letter B here, let's go ahead and start with our probability. We're saying what is the likelihood that a random score, or we're going to use x to represent our x values down here, is greater than 67 here. And so what we're looking at is saying, well, if 67 is right here, then perhaps, and I'll change my color here, then perhaps we're looking for the scores that fall above 67. So when we add all of this up right here, we could say that, well, we know that this section here is 13.5%, okay? This subsection right here holds 2.35% of the population, and everything beyond that is about only 0.15% of the population. So adding these up, we'll just grab our calculator here. We could say that our 13.5% plus our 2.35% plus our 0.15 adds up to about 16% of the population. So we could say that there's a 16% of the field is going to be eligible to be hired by the agency here. So essentially what I want you to do for this extra example number 2 is pause the video, and I want you to draw your own curve. Now we're using the same data that we used up here, so you can redraw the same curve, but I want you to answer these questions about it. And when you're ready to answer these questions or see if you got your questions right, go ahead and unpause the video. But when you're ready, let's go ahead and take a look at this. I'm going to re-sketch my curve here. We're going to say that we'll redraw in my bell here, and we should really redraw this every time. It's just that, I was being lazy here. We say our average score is 55, so going 3 standard deviations above the mean and 3 standard deviations below the mean, we saw these scores 19, 31, 43. Up here we had 67, 79, and 91. But if we said, how likely is it that, or what percentage of the people lies between a 31 and a 55? Let's start with this. We're going to write this probability as 31 is less than or equal to x is less than or equal to 55. In other words, our score is between 31 and 55. And so we can see on this illustration here, if I switch kind of back over to my yellowy color here, let's go orangish. We could see that 31 is right here, okay, between 31 and 55. 55 is the average, but what percentage of scores lies between the average and 2 standard deviations below the average? Remember, because of our empirical rule, that 34% of the population has to lie here, and 13.5% of the population has to lie here. So if we want to know what this total area is, we'll just sum these together. So we get 13.5 plus 34, so we get 47.5% chance, a 47.5% chance. Now, to look at letter B, you should have drawn your picture out here with your normal distribution, okay, with our average in the middle, and we'll go 3 standard deviations below the mean and 3 standard deviations above the mean. So we have 55, 67, okay, 79, and 91 with our standard deviation value there. And we say 43, 12 below 43 is 31, and 12 below this is 19. So we could see that, let me make that again, 19 here. We want to know, if an agency in the state will only hire applicants with test scores of 79 or greater, about what percentage of the people have test scores to make them eligible to be hired by the agency. So again, we're going to write this probability, what percentage of test scores, or x value down here, random x, is greater than 79 or greater. So we say 79 or greater would be this value here, and we would shade this portion of the curve here. I didn't shade over here because I was writing in the values, but shading this portion in over here, we would see that we have this right here, 2.35%, plus the other out here on the edge. Everything to the right of that is only the leftover 0.15%. So adding those together, you can see that we get a 2.5% likelihood that this happens here. So for this part of the video, what I want to have everybody do is basically pause it and attempt all these and try to find these values here in the pure sense, and then also answer this question G. When you're ready to go, we'll go ahead and have you unpause the video here. Looking at letter A. Letter A asks us, finding the indicated probability for a randomly selected x value from the distribution. It says, how likely is it that some given x value down here is less than mu? In other words, less than the average. So if we were to look at this here in terms of our normal distribution here, we would say this being the average, then less than the average would be all data values that lie to the left of this right here. And so because we have everything to the left of this, and because the whole curve adds up to an area of 1, we could say that adding up all the population below the average should give us 50% of the population right here. We could also have obtained this by adding these 4 values together here. Now when we look at this next value, it says what's the probability that our random x value lies above the mean. I hope you can see that in this particular case, we would say here's our mean, 3 standard deviations to the right and 3 to the left. We'd say everything above the mean, if we're shading this right here, would also be the other 50% of the data right here, and that would make reasonable sense. So now looking at these last 4 examples here, we would have to sketch out what it is that we're trying to find it looks like in this example here, we're trying to find the likelihood. Here's our mean. We'll go 3 above the average and 3 below the average. The excuse me, the likelihood that our mean is bigger than the average, where our average is right here, but less than our mu plus 2 sigma, or our mean plus 2 standard deviations to the right. So to go 2 standard deviations to the right, we're talking about this subsection right here. And so it looks like we would have our 34% plus our 13.5%. This would give us 47.5% of the population would have to lie between the average and 2 standard deviations above. So these last 3 here, oops, I forgot a parenthesis here, we'll sketch these in. We look like on this one here, here's our average, 3 above, 3 standard deviations below the mean. This one here, we want to know how likely it is that our x value is between 1 standard deviation below the mean, which would be right here, and the mean itself. So looking at this section right here, we should have obtained 34%. Now, this next example here, sketching this out, we are asking how likely is it that our x value is less than 3 standard deviations below the mean. So given that this is our mean and we're going 3 standard deviations below, we're saying that we want to know how likely it is that our x value is less than this, occurs to the left of this right here. So this is an interesting situation where we would say that using our empirical rule, we know that everything from 3 standard deviations out on the side to the left here would be only 0.15% of the population, or a very small percentage of the population. And lastly, this one here is asking how likely is it then that our random x value, here's the mean, we'll go 3 standard deviations above and 3 standard deviations below, but that our mean is randomly, excuse me, our x value is randomly chosen to be greater than 1 standard deviation above the mean. So the mean plus 1 standard deviation is this x value right here. We want to know how likely it is that our x value is above this. Again, what we'll do is we'll add on, using our knowledge from our empirical rule, this subsection's area, which is 13.5% of the area. Here is 2.35% of the area. And this last subsection is 0.15% of the area. So summing all of these together here, we could see that this would be 13.5 plus 2.35 plus 0.15, which gives us 16% of the area. So now for this last question, you should have read through this, and it says in example 2, about what percentage of the people taking the test can be expected to have scores between 43 and 79. I'm going to cheat a little bit here. I'm going to come back over and I'm going to say that, well, if I had drawn my picture again here, if I had, 43 and 79 would have been these 2 values right here. So the likelihood that we would have grabbed randomly a person who tested between these scores right here would be the area under the curve between these. And we can see that we get a 34% section, a 34% section, and one of our 13.5% subsections. So we would get 68 plus 13.5 here. 68 plus 13.5% of the population is 81.5% of the population there. So to answer this question, we would say the probability that our score was between, our x value was between 43 and 79% is, and let me pull my calculator up here again, 81.5% of the population. Cheers.